Hello, everyone. Let me start with a quick introduction about myself. I'm a qualified fellow actuary and have 6.5 years of experience in teaching actuarial science professionally, as well as I've worked across different actuarial science verticals across the 6.5 years. That was a very brief introduction about myself. Before I proceed to the solution discussions, let me inform you that the new batches for IFoA April 2025 and II May 2025 start from 6th of October. Do note that we have a single batch and limited capacity for each paper. So enroll and start early, because at Finatics we believe that if a student starts early, they get ample amount of time for preparation and a buffer time as well at the end to meet any unforeseen circumstances. I hope the solution discussion with you helps you. Hello everyone. So in this video, we would be discussing CS2 Paper B September 2024 solutions. The paper seemed to be quite straightforward this time, not something tricky, or even all the machine learning questions were quite straightforward. So let's see. First question is, insurance company launched a new product over a year ago and the data set shows a number of products sold each day. The company is looking into using this data to forecast sales volume for future months. Construct R code to load the data into R, assign it into a data frame called sales data, and display the last 5 rows of the data set. So I just import the data, and the last 5 rows is tails of sales data, comma 5. Then construct R code to check if the values in the column labeled day are in ascending order. So I've just created a Y vector, and I have created a loop to check that each value from 1 till the end is less than. So 1 is less than 2, 2 is less than 3, and so on. And if all of them is true, and the last value, since it will be a NA because the last value will not get checked, so NA.RM is true, then print yes in ascending order. Okay. Then construct R code to plot suitably labeled line graph of the number of products sold over time. So this is a basic plot with type equals to L because it's told a line graph. Okay. The next part is comment on the plot above. There seems to be a multiplicative trend in the data after every 100 days, if you see 100 or 200 days. Okay. 200 days actually, after every 200 days, there seems to be a repercussion. Let the product sold K, so basically K is in italics, denote the vector obtained by differencing the sales volume K times. First is 0 times, then 1 times, then 2 times, and assess the stationarity. So for 0 times, if we see pp.test, sorry, we have extra bracket, pp.test, it is p-value is greater than 0.05. That means this data is not stationary. Okay. Now I difference it 1 time and I see the data is stationary since it's less than 0.05. Difference it 2 times and pp.test sold to, again the data is stationary, but we need to see whether how many times you need to difference the data. Also, it's a suitable test. It's a 7 marks, so you should check whether the data should be differenced 1 times or 2 times. So if you see the variance of differencing 1 times is 21, whereas variance of differencing 2 times is 71. Since the variance is increasing, that means it is okay if we difference it 1 time also. Okay. Next part, the company would like to investigate the model in the form of P2Q. So they are wanting it to differentiate 2 times for the products sold, where P and Q can take the values 0 to 3. Construct an R code to fit ARIMA P2Q models to the data for all possible combinations of P and Q, and store the values of AIC in a 4 into 4 matrix named AIC matrix with appropriate row and column names. So I created a AIC matrix of 4 to 4. Okay, and values are all NA. The row names are P and 0 to 3, and column names are Q equal to 0 to 3. Okay. Now, ARIMA model is for P in 0 to 3, Q in 0 to 3. Model ARIMA sales, data dollar products sold, order is equals to C P to Q. AIC matrix, whatever P plus 1, Q plus 1 is the AIC model, which we have stored. Okay. and this is the AIC matrix. So P equal to 0. As it increases, it gets stored from 0 to 1 and so on. So all this matrix for Q, P equal to 0, Q equal to 0, P equal to 1, Q equal to 1, these values get stored. Identify the most appropriate model for fitting the data to according to AIC. So obviously we have to find the minimum AIC. So we'll say which AIC matrix is equal to minimum of AIC matrix and array inclusive true. So basically we are doing it in an array. So it's taking array index. Okay. So now the answers will display minimum of AIC minus 1 and min. So if you see best P will be 1. We are doing minus 1 because our values start from 0. Okay. So it will, the counting starts from 1. Hence we have to do minus 1 so that we get the best model, that is 1 and 2. Okay. So our best model concatenate is ARIMA 1, 2, 2. Now forecast, next part is construct an R code that the model identified in part 7 to forecast the sales volume over the next 60 days, storing the forecast values in a vector called forecast volume and display the first 10 values of the forecast. So forecast volume is predict best model n dot ahead is equal to 60 from the best model. Sorry, I did not run best model. And then forecast predict for the first 10 values. Now they say plot a graph showing the forecast sales from part 7. So we have drawn, this is the original data and this is the forecasted value. You can also only draw the forecasted value. That is also perfectly correct. Comment on the plot. It shows a steady trend with expected variations. If you see, it is rising again for the next 60 days as it was supposed to rise. So it is following the similar kind of a trend. So quite simple time series question. Next question, an insurer is analyzing the price of the pet insurance policies. In this instance, the analyst is assessing mortality rates of a particular breed of cat. Mortality data in respect of the breed of cat has been collected from a recent 2-year investigation. The raw data in respect of each cat is found in the file mod data 1.csv. The dataset includes the exact age of the cat when observation commenced and ended together with the following indicator variable in whether the cat died during the observation or not. Whether the cat died equal to 1, whether the cat survived died equal to 0. The aggregate exposed to risk and the number of days split by age last calculated from this are shown below. Construct an R code from this, saving it as a data frame. So load the data. So I've loaded the data mod data and head of mod data. You can just see. So we have the observation start, end, exposed to risk, died, and the cat number. Construct an R code to verify the ETR values above in the respect of each integer age from age last from 0 up to 9 years. Save the ETR vector in a model called ETR1. So ETR1 will be not this. So we have ages equal to 0.9. ETR1, I'm creating a vector which is empty. Now I'm taking for I in 1, 2 ages. Age start is I, age end is I plus 1. Then we have to calculate the overlap between age start and age end. Okay, so P max 0. Then we have to calculate a P min of the mortality data dollar observation end age and age end, which is the whatever is our starting age, and minus P max of mortality observation of start age, comma, age start at the age start. Okay. So you have to calculate this overlap to find the ages in this loop, and then each ETR will be calculated for that age as a sum of all the ages. Okay, basically age last birthday needs to be calculated from the given observation start and end age. Data.frame, I have created a data.frame to see the ETR. So it's see 0 to 9. And if you match the values from here 1 to 5, 6, 5737, 15630, 1713. So all are matching. So we have verified. Next is construct an R code to verify the above total number of deaths in respect of each integer age from 0 to 9 years. Save the death in a vector called death summary. So again, ages, and I've created death summary. Same code, now only do it for deaths. Okay, if diet is equal to 1 and the observation end age is greater than the age start and the observation end date is less than the age end also, then only that person is in the observation and you have to only find people who have died in the observation. Okay, and then find a death summary. And now if you match 1256, 1256, 3996, 5770, 1531, it's all matching. Okay, this is a similar thing which is done in the class as well. Generally for exposed to this, similar type of code is used. Calculate the crude rates for each age. So crude rates is death of summary dollar deaths divided by ETR $1 ETR. Okay, it will give me the crude rates. Then I have two tables which they have said are established using this, and then save them to as table 1 and table 2. So I'm just importing the two tables. Now they've just asked to plot the crude rates and table 1 and table 2 together in one plot and show the crude rates as points and the table rates as different colors lines. So I've taken ages to be one of the table's ages and then plot. So this is the plot you get as points. Then line is red color for table 1 and for table 2 is blue color, and I put a legend to it. Okay, so it's a labeled graph properly. You should do, then only you will get 4 marks for this. The insurance company first wishes to test the null hypothesis that the rates in table 1 represent the true mortality rates of the cats. Construct R code to complete the following 3 statistical tests of the null hypothesis and state the conclusion of the test. So you have to do the test for the table 1. So I've calculated expected deaths, which is ETR into the mortality rate mu. Okay, then the observed deaths is what we have. Chi-square test statistic is observed minus expected divided by expected. And we get the chi-square statistic. Degrees of freedom, you can take 1, you can take 2 as well. Okay, so I've taken 1 and you see the test statistic is much greater than the value. So hence we reject the null hypothesis. Okay. For the serial correlation test, again, I've calculated residuals, which is ZX. You have to calculate M, which is the end row of total number of tables. R1 is, you can use the ACF of residuals lag dot max plot equals to false. Okay. Observe dot test dot stat is SQRT of M into R1, which is the statistic we have. And then we have 1 minus P norm, which is the finding out the P value for this test statistic. So if you see the test statistic for this value, it comes out to be 0.0265, which is less than 0.05. So we reject H naught here as well. The third test which has been told is the signs test. So signs test will find out the signs of ZX. So signs of ZX, it will tell us how many, now we'll find out how many sign changes are there. So we'll find out the sums of signs -1, which is not equal to the length of signs, minus length of signs. There is total 1 sign change, which is totally fine. And we find the binomial test because it follows 0.5 distribution. So if you see here, it is also 0.02, which is less than 0.05. So we reject H naught. So for all table 1 mortality rates, as for the graph also, you can see the table 1 is quite lower. Okay. Now we have to repeat the same thing for table 2. Construct our code to repeat the 3 tests in part 5 for the null hypothesis in table 2. So just copy the codes and run it for table 2. Same codes. Now if you see, this is 16.03 and degrees of freedom. This is 16.91. So we accept the test because test statistic is less than the critical value. Residuals again will remain the same. N row of table 2. Okay. R1 you calculate. Observed. And 1 minus P norm. So it's a 0.598, which is again greater than 0.05. So we accept the test. Signs also, you do the same thing. So you see this is 0.34, which is greater than 0.05. So here also we accept the test. So for all the mortality rates of table 2, we accept, but for all mortality rate of table 1, we reject the test. Question 3. Alpha Advisors are a small firm investment consulting advising on the selection of investment funds. An analyst at Alpha Advisors is conducting research on the investment return after fees of 50 funds that invest in emerging markets. The data collected on these funds is found in the file. Fund and ID number, return percentage, rating, risk, size, experience, inflow, holding, turnover is given. The analyst seeks to understand the main factors affecting investment returns in the last year. Construct R code to load the dataset from question 3 data CSV into R, saving it as a data frame called fund data and display the first 9 rows. So to display the first 9 rows of the data set, first we need to load the data. So read.csv and then first 9 rows is head. Okay. Then they say construct R code to build a multiple linear regression model for return as the response variable and rating, risk, size, experience, inflow, holding, turnover as the explanatory variables and display the results. So model is LM and return follows rating plus risk plus size plus experience plus inflow, holdings, turnover. Data is equals to fund data. And model is this. So this is the result, and you find from the summary of model, you see what are the significant factors. Okay, so you have to display the results. Alpha advisors claim in their own marketing materials to have a skill in the selecting better performing funds using their rating. Comment briefly on this claim based on your output in part 2. So they have skill in selecting better performing funds using their rating. So if we see the rating factor, it is not significant because it is greater than 0.05. So the rating might not be a strong predictor of returns. Okay. Next, explain why it can be useful to work with rescaled explanatory variables with zero mean and standard deviation of 1. So if we rescale it, then it allows coefficients to be interpreted as a change in the response variable for one standard deviation change in the explanatory variable. This makes it easier to compare. It allows coefficients to be interpreted in that way. It improves numerical stability of the regression model when predictors on different scales. This helps in convergence of algorithms, and standardization can reduce the impact of multicollinearity when predictors are highly correlated. Okay. Next is calculate the standardized versions of each of the 7 explanatory variables and build a multiple linear regression model with standardized explanatory variables. So for standardizing, you just need to do a scale. Okay, scale parameter standardizes it between 0 and 1 and then create a model. First, we have calculated the standardized versions now. Now, construct R code to so then build a multiple linear regression model. So this is the multiple linear regression model. And again, we display the summary, which is this. Okay, after we did a standard model. Then construct R code to calculate the sum of squares of the regression coefficients for the model in part 5 and store it as the value as penalty. So coefficients will require, and penalty is nothing but sum of coefficients minus 1 square. We'll not take the intercept, only the coefficient square. Okay, this is the sum of squares of regression coefficients. Okay, 2.17. One way of applying ridge regression techniques is to seek a linear regression model that minimizes the penalized sum of squares given by RSS minus lambda beta I square, where RSS is the residual sum of squares of the regression model and beta are the regression coefficients for the model and lambda is our 0. Okay, determine the values of lambda for which a simple linear regression model with only the rescaled alpha advisor rating as the explanatory variable has a lower penalized sum of squares than the full multiple linear regression model by calculating the penalized sum of squares for these two models for lambda equal to 0 to 10. So we'll take 0 to 10, 11 variables. So we've done, we created 4 variables. Model simple is only with rating standard, and we find the regression square, and for lambda equal to 0 to 10, you do the same thing. Okay, and you find the result and print the results. Penalty simple and penalty full. The head of marketing advisors wants to run advertising with the headline, all you need are our alpha ratings, claim that the rating alone can be used to determine better performing. So if we see consistency of the simple penalty is not always less than the full penalty, so it might be not good always. Okay. So it might not be good for this person to use this advertisement at all times. So this was the basic code of the linear regression model and or CS2 paper. Thank you.